And the way I treat it is just like I do with my lab reports. If I go to grade the extra credit assignment and it's there, then you get full credit. If you try to do it after the due date and but before I grade it, then nothing is wrong with that. And probably I'm probably never going to take off late points for extra credit. Uh, but if you try to do them after you finish the final or after you finished even the last face-to-face test, that might not be a time where I'd take it that late. So I just try to say, if you do it around a week or so within the material or within the week that it's actually assigned, then I won't have any problem giving you full credit no matter how late it is. So just like I said, try not to let it go more than a week or two because the whole purpose of the extra credit is for you to learn for that particular chapter. So if you do it later in that chapter, it's not going to help you. For those of you who are not knowing what I'm talking about right now, one student asked me if I could change the due date because I'm an idiot and I opened the online extra credit assignment and made it a quote unquote made it available, but I never changed the due date. So it said January 20 of 2026, and obviously no one could turn anything like that. So I did change that. But what I was telling the student is that the way my extra credits work is I certainly would not mark it late if I haven't graded it yet, even if it's past the due date. But once I grade it, if it's not there, that's the time that I would consider a late penalty. But I just can't imagine a scenario in which I would even do a late penalty. I just want you guys to make sure y'all try to do the extra credit that I give you in a given week within the next week or two, just because the whole purpose of the extra credit is to help you with the chapter that I'm working on when I offer it. So it's a learning experience just like the practice test. That's why once you've taken the test that the practice test is for, I'd never give you the extra credit for the practice test because the whole purpose of me giving you extra credit for the practice test is to use it to help you better understand the material that's going to happen on the test and therefore make a better grade. So just keep that in mind. It is past the time now. It's 5:33, so we're going to go ahead and get started. I will remind everybody to go ahead and chat me your first and last name if you haven't done so already. It looks like most everybody has. I've got about 13 people in here. That's great. Anybody have any questions before we get started? You may just blurt them out, or you can type them over here in the chat area. Over here seems perfectly reasonable to me, but y'all aren't seeing my hands, you aren't seeing where my eyes are pointing or anything, don't know anything about it, so it's kind of a goofy thing for me to say. I don't think I do very good in radio because I tend to say stupid stuff like that. Like, look, look, what good's looking going to do if you're on the radio? All right. Okay, so what we're starting today is chapter four, and chapter four is called dynamics, Newton's laws of motion. So, in this chapter, we're going to learn Newton's laws of motion. Your book does it in a slow, progressive way where basically you first off learn Newton's first law, and then he gives you a couple examples about Newton's first law. Then he gives you Newton's second law, and he works a couple examples about Newton's second law. And then he gives you Newton's third law, and again gives you a few examples. I like to just go ahead and get the laws out of the way and get jump into doing the examples. I hemmed and hawed a little bit longer than I normally like to on my last night version of this lecture, and it ended up not getting as many examples done. So that's not necessarily the most fruitful way. Of course, I always try to tell some of the colorful history. I'll try to avoid that a little bit too. But if you want to see any of that stuff, including I think I made a mistake by saying Galileo did something that he didn't do by mistake. So, but I corrected myself in real time. So, anyways, with this chapter, we're going to learn Newton's laws of motion. And you probably heard historically Newton said, "If I have seen further than others, it's only because I stood on the shoulders of giants." And that's sort of a truth, a truism. It sounds very humble of Newton. And if you know anything about Newton, he was not a humble person. Just like Galileo, he was not humble either. In fact, brash, confident, cocky, arrogant, that those kind of phrases would normally be what was used regarding Galileo as well as Newton, and a lot of great minds, to be honest with you. And I don't necessarily say that gives them a pass. I think you should be respectful, but I certainly understand you should also have confidence. You know, is it arrogant for instance, a friend of mine told me it's not arrogant for Cindy Crawford to think she's beautiful. Of course, she's a bit older now, and maybe some people wouldn't find her still as beautiful as she was, but she clearly was an upper echelon of beauty in terms of just everybody that we know on the planet. So, no, there isn't. It's not cocky or arrogant for someone of that stature to consider themselves to be beautiful, but there is a limit to how you should treat people. So I'll just keep that in mind. But anyways, what I wanted to give you is a backstory regarding that. If I have seen further than others, only because I stood on the shoulders of giants. Part of it was the fact that Galileo, after facing the Inquisition, was put in house arrest, and during that time, he chose to study motion because he was forbidden from studying how the planets move or from making statements or publications about how the planets move. And he had already discovered that the laws of science, as we knew at the time, by according to the teachings of Aristotle, were already in error, and we didn't necessarily understand motion. So he decided to study motion, and in that process, he studied motion and discovered, or more or less, invented the concept of constant speed, or maybe even constant velocity. There was no concept of vector in the time of Galileo, nor was there any time of concept of vectors in the time of Newton. In fact, vectors didn't really come into play as a real thing until somewhere around the mid 1800s, 1830s, somewhere around there. So all the stuff that we know of as vector calculus, absolute calculus, all that stuff never really came along until at least the 1820s and 30s. Vector calculus was more or less invented independently by two people. Uh, One of which was Oliver Heaviside, who was one of the Maxwellians that got Maxwell's equations to be so famous, and the other one, I can't remember his last name. He was actually American, and one of the energies that we learn about in quantum mechanics, I mean in thermodynamics, is named after him. I want to say it was Gibbs, as in Gibbs free energy. I might be misremembering that, but it's one of those guys, and I think his first name was Joseph for some reason. I don't even know why I know his first name, but him and Oliver Heaviside simultaneously invented vector calculus slash discovered vector calculus, and that would have been, like I said, circa 1830s to 1860s. So we didn't have any of that kind of stuff. With that in mind, what I will tell you is that Galileo came up with the idea of what we now call constant speed. And he would say basically an object moving with a constant speed or constant velocity is an object that travels a fixed distance in a fixed amount of time. So if you choose a fixed amount of time, for instance, of 1 second, and you measure the motion of an object and it travels 5 meters in that 1 second, and then you look sometime later and measure out how far it travels during another 1 second interval, and you find that's 5 meters, then you would reach the conclusion that that motion is probably a motion of constant speed or constant velocity, and specifically that velocity would be 5 meters per second. Okay. Now, there is a possibility that just by measuring two, you could have happened to find the two instances where 1 second of time resulted in 5 meters of distance. And if you'd like check the second immediately after, it would have been different, or the second immediately between the two, it might have been different. So, in principle, that's really what the definition of constant speed is that it moves a fixed distance in a certain amount of time. If you wanted to dial it back and say every tenth of a second, then every tenth of a second it would have had to have moved zero point 0.5 meters, or if you do every hundredth of a second, it would have had to move 0.05 meters, and all of those would result in 5 meters per second. Galileo also discovered that objects in acceleration, constant acceleration, he's the one that more or less defined that terminology as well. They change their velocity by a fixed amount in a fixed amount of time. So when I say, for instance, the acceleration of gravity is about 10 meters per second every second, and I'm doing that approximation for a purpose because it's a lot easier to talk about 10 as opposed to 9.80. So when we say the acceleration is about 9 or 10.0 meters per second every second, what we mean is because according to Galileo, each second the velocity will change by 10 meters per second. So in the first second, it's going to change by 10 meters per second. In the second, it's going to change by 10 meters per second. In the third, it's going to change by 10 meters per second. Or you might even go to the tenth of a second, in which case it'd change by point 0.1, or excuse me, 1 meter per second each tenth of a second, or 1 meter per second the next tenth of a second. Or if you went to a hundredth of a second, it'd be zero point 0.1 meters in a hundredth of a second, and then zero point 0.1 meters in the second hundredth of a second. That is constant acceleration. And he went further on to say that when an object starts from rest and undergoes a constant acceleration, its distance that it travels is proportional to the square of the time. So that when you double the time, you don't double the distance, you actually quadruple it because 2 squared is 4. If you triple the time, you don't triple the distance, you nine-tuple it because 3 squared is 9. If you quadruple the time, then you 16-tuple the distance. And if you quintuple the time, you 25-tuple the distance, so on and so forth. So all of that was given to us by Galileo, and he came up with the idea that acceleration due to gravity is in fact a constant, and he was even able to work it out to equivalent to the modern day 9.80 meters per second every second. And he found that that was a constant, unlike what Galileo had learned from Aristotelian texts. So before that, we were all beholden to the teachings of Aristotle. The whole scriptures had all been interpreted in terms of the science of Aristotle. And therefore, when you start to say, hey, uh, here's some laws of physics that are different from what we know of Aristotle, you're obviously going to bump heads with the portions of it that were related to the Bible. So that's why the church often got involved with this sort of thing, because they had very important things that they didn't want to be shaken up. And I say that in the most positive way I can. I don't think any of them were necessarily trying to be evil. They just, knew that there was a slippery slope and that sort of thing. So, with that being said, we now know that Galileo did a lot of this stuff. And when I say if I have seen further than others, or when Newton says if I have seen further than others, it's only because I stood on the shoulders of giants. One of those giants he was referring to was Newton, or excuse me, was Galileo, because Galileo, in fact, had found what we now call Newton's first law of motion, and he had called it Galileo, or we had called it Galileo's law of inertia. It basically what Galileo said was it's as if an object has this quantity he called inertia, a reluctance to change its motion. And in fact, the natural thing is that objects do not tend to change their motion. In fact, they will move in a straight line at a fixed speed forever unless acted upon by some force. And his use of the word inertia was sort of just a way of making himself feel a little bit better about disagreeing with Aristotle, or making other people feel better about disagreeing with Aristotle, because Galileo was not necessarily concerned about upsetting one of the ancient, godlike figures of science, namely Aristotle. So he did come up with something the equivalent of Newton's first law of motion, but Newton later did that as well. Not only that, I was telling my students last night, I was in Salt Lake City, Utah at a time when Leonardo da Vinci's notebooks and various things were traveling the planet so that we could go to various museums, depending on where you were, and see some of da Vinci's stuff. And I got to look in one of his notebooks, and I saw this sentence, and it basically said, it is obvious that when an eagle pushes down on the wind, on the air with a force of 50 pounds, then the air pushes back up on the eagle with a force of 50 pounds. That is Leonardo da Vinci saying Newton's third law of motion. Now, what Newton did do from whole cloth and make up on his own is Newton's second law of motion, and then he codified it by showing a very rigorous interpretation of how you can apply Newton's laws of motion, as well as Newton's law of gravity, as well as Newton's calculus, to physics problems, as well as a buttload of geometry, because he didn't have access to scientific calculators and quick approximations and stuff like you could do with a calculator nowadays. So he literally had to do all of his proofs with geometric proofs and stuff of that sort. So now that I've given you a little bit of that background history, I will tell you the other side of the, if I have seen further than others, only because I stood on the shoulders of giants. It was said specifically in front of the Royal Society, of which the leader was a guy by the name of Robert Hooke, who was an arch enemy of Newton, and in fact had multiple occasions accused Newton of stealing his work and stuff of that sort when history basically shows that if anybody stole at work, it would have been Robert Hooke had stole it. But we really don't have any evidence of Hooke stealing it either. We just have evidence that Hooke claimed to have done something that Newton did, and Hooke could never bring the goods to show us that he actually did it, but Newton did bring the goods. So that's how that worked out. But either way, the main thing was Robert Hooke was an enemy of Newton's, and he had a bit of what we call a short man complex in that he was probably maybe 4'8" or 4'10" or something like that. So when Newton says, "If I have seen further than others, it's only because I stood on the shoulders of giants," he's saying, "Not standing on the shoulders of hobbits like you, Mr. Hooke." So maybe that makes it a little sound a little more reasonable, knowing how haughty and cocky Newton was. Uh, so I'm going to go ahead and start off with Newton's first law of motion, and I've copied down into my notes. I've copied the version that your textbook is given, just so you'd have a version. What you guys have, as I've been preaching to you, whenever you learn in a textbook that there's something called a law, or whenever a certain concept as is so important that a whole chapter or even a whole subsection of a chapter, if that's the case, where a whole subsection of a chapter or even bigger, a whole chapter has been named after a certain concept, then you better, as a bare minimum, memorize that concept. Okay. That's what I'm saying here. So Newton's first law of motion is an example, Newton's second law of motion is an example, and Newton's third law is an example. And all of those are ones you should memorize. I do think, even though I'm not requiring you to memorize verbatim exactly the wording, you should be able to paraphrase it correctly and accurately and precisely enough. So, for instance, one of the things about Newton's second law that is said is not only that the acceleration is directly proportional to the net force and inversely proportional to the mass, but the fact that the acceleration is also parallel to the net force acting on the object. So you can memorize that sentence verbatim, or you just got to make sure you get all those points across to me with whatever sentences you use. And to be honest with you, most of the time when I ask these questions, it would be along the lines of maybe you have A through Q are just a list of sentences. And some of those sentences are complete hogwash, but other sentences are like the first law of thermodynamics or the zeroth law of thermodynamics or Newton's first law of motion or Newton's second law of motion or Newton's law of gravity or Maxwell's equation or something like that. And then another column, you'll have names of various principles and laws, and your job would be to match it to them. So you should at least be able to recognize the wording of these things and identify them as not only a law of Newton, but specifically the first law. You should be able to pick that out from the second law, and you should be able to pick that out from the third law, and you should be able to discern all of those from Newton's law of gravity, and so on and so forth. Same thing with the thermodynamic laws. Once we get to the second semester of this course, we'll cover the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. All of those things are things you should commit to memory well enough that you not only know what they are, but you know which ones are which. Uh, this semester, we're also going to have Kepler's first law of planetary motion, Kepler's second law of planetary motion, and Kepler's third law of planetary motion. So those are some more examples. Now, to get started, let me go ahead and share my screen with you, and I'm sharing my iPad screen. We will be working examples from the book, so it is best for you to have your textbook, or at least your e-version of your textbook available when you, ooh, why is this not working yet? Hold on. While we're doing these examples, I will be reading the questions from the examples out loud, but you might need to look at it to be better off. So definitely have it open. It looks like I might be on my wrong Wi-Fi. That's why it's not loading. That does appear to be the case. Sorry, it's going to take a second. Okay, I got that one. There it is. My iPad and my computer have to be on the same Wi-Fi or I can't share. So now it should work. Okay, finally got that done. So you can see Newton's first law. Every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. This is Newton's first law as Giancoli says it. I normally say something along the lines of an object in motion tends to stay in that state of motion unless acted upon by a net external force. I say net because you have to take into account not just a particular force acting on it, but all the forces that are acting on it. I say internal because it doesn't, external, excuse me, I said external, because a force on M as a result of another part of M would not count. That's an internal force. So when we apply Newton's laws of motion, we have to be very specific about what the a law is being applied to. Is it the single ball, or is it like the ball that's attached to a rod that's attached to another ball, and therefore it's all of that, the ball, the rod, and the ball? Or is it, several balls, or is it a flock of seagulls, that sort of thing? So if you're talking about it like a flock of seagulls, then a force on one seagull as a result of another seagull is not an external force. That's an internal force, and therefore it doesn't go on the left-hand side of Newton's second law, which we'll learn later. So again, I say an object in motion tends to stay in that state of motion unless acted upon by a net external force. So the net external force has to obviously be different from zero. And if it is different than zero, then the object will not continue to move in uniform motion. Now, we can shorten all this by just using the word constant velocity or the phrase constant velocity and remembering that velocity is a vector quantity. Because when I say an object will maintain a constant velocity unless acted upon by a net external force, I'm saying that the object will not change the speed or direction of motion unless acted upon by a net external force. And that speed and direction of motion could include a speed of zero with no direction of motion. Okay. Not only that, there's a certain amount of logic that can be applied to it. So, for instance, one thing we might do is rewrite Newton's first law in terms of an if-then statement, and then there's certain things you can do to an if-then statement. For instance, you can do the contrapositive, you can do the converse, and you can do the inverse. And the contrapositive is always equivalent to the original statement. So things like that can be used when you go to analyze Newton's first law, and you can make conclusions like, oh, if the object is not moving with a changing velocity. In other words, if the object has a constant velocity, then that allows us to reach the conclusion that the net force acting on the system is zero. And if we already know, for instance, that there is at least one force acting on the system, then using that conclusion that we just made, we can conclude that there must be at least a second force as well, because if there was just one force, then there's no way that force could be zero or it wouldn't be a force on it. So you got to sort of play that game a little bit too to further understand what this means. So Newton's first law can be shortened to basically say an object will maintain a constant velocity unless acted upon by a net external force. Newton's second law is saying, hey, what if there is a net external force that's not equal to zero? Then what happens? And the way your textbook author is saying it is he's saying the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to the object's mass. The direction of the acceleration is in the direction of the net force acting on the object. So notice it not only addressed how the acceleration was related to the net force in terms of being directly proportional. What that means, for instance, is if you double the net force acting on the system, then you're going to double the acceleration. And if you triple the net force, then you're going to triple the acceleration. That's what directly proportional means. Okay. It also says that it's inversely proportional to the mass. And what that means is if the mass doubles, then the acceleration is going to go down by one half. If the mass triples, the acceleration is going to go down by one third. Now, the third thing it says that the acceleration is directly, or excuse me, is in the same direction as the net force. And if you write this in equation form, as I have written down here, you can see that in equation form, it's actually in a vector equation, so that it says the A vector is equal to the summation of the forces vector divided by m. Well, the summation of the forces is a vector sum, and therefore it has a magnitude and direction, just like the acceleration with a vector symbol over it has a magnitude and direction. And for a vector equation to be correct, it has to be true that the left hand side and the right hand side have the same magnitude of a vector, and that the left hand side and the right hand side have the same direction as each other. So, with that in mind, you can see that A must be in the exact same direction as the summation of the forces divided by M. But remember, M is mass, and that can't be negative. So, we're basically just taking a vector and dividing it by a scalar. And if the scalar happened to be a negative, then it would change the direction of the vector by 180 degrees. But since the mass can't be negative, it can't change the direction at all. So clearly, the summation of forces, whether it's divided by mass or not, is parallel to the acceleration. And then I also showed how we could write this in the typical way that most people use Newton's second law, which says the summation of the forces on the left is equal to the mass times acceleration, and that's on the right. And since that's a vector equation, that can be broken up into three component equations where the summation of the x components of the force is equal to the mass times the x component of acceleration. The summation of the force of the y components of the force is equal to the mass times the y component of the acceleration, and the summation of the z components of the force is equal to the mass times the z component of acceleration. Now, since we're talking about components, that means these az, ax, and ay, and fx, and fx number 2, fx number 3, fy number 4, fz number q, or whatever, all of those can be negative as well. There's not such thing as a negative magnitude of a vector, at least not right now. And because of that, I want you to understand that it is okay to have forces that have a negative sign when you're using it in this form, because in this form, the vectors that we're talking about, we're working with their components, not with the total vector. Okay. So that's Newton's second law, and it really tells us, hey, if I double the total force acting on a system, then I should be able to double the acceleration. If I triple that force, I should triple that acceleration. If I cut that force by 1/8, then I should decrease the acceleration by a factor of 8. Notice all of these are talking about multiplications. There's no addition when I talk about proportional and inversely proportional. Then the third law, which seems almost useless, but as I'll show you later, it turns out to be very important. In many cases, you can't apply Newton's second law if you didn't know Newton's third law. So you'll see that a little bit later. Newton's third law, as your book states it, is whenever one object exerts a force on a second object, the second object exerts an equal force on the in the opposite direction on the first. I like to write this in equation form, and therefore I would say that sentence that I just read to you says the vector f21 is equal to the negative of the vector f12. Now, let me read what that f21 really should be read as. So this vector equation says the force on object 2 due to object 1 is equal to the negative of the force on object 1 due to object 2. So that's how you read that terminology. When you have two subscripts on a force, the first subscript is the thing experiencing the force. The second subscript is the thing causing the force. So F1 or F21 means the force on object 2 as a result of object 1, and the F12 means the force on object 1 as a result of object 2. You could also rephrase this to every action there's an equal but opposite reaction, and that's the more typical way we've heard it, and that's important as well. But all of those are acceptable versions. The main thing to understand is one, you have this idea of action reaction pairs because Newton's second law or third law can often be said in terms of action reaction. For every action, there's an equal but opposite reaction. The action reaction pair, because of this equation, you see are related to each other. I've got F21 is equal to negative F12. So if you want to identify an action reaction pair, they have to be acting on each other. So for instance, if you say, what is the reaction pair to the force that pulls Mr. Younger down from a curb? Like if I go to step off a curb, there's a gravitational force pulling me down towards the ground. That gravitational force, which we'll learn in chapter 6, is the force of gravity from the earth. So when I'm pulled down off of a curb with a force of around 250 pounds, that is the force of the earth on me. So that's the force on me as a result of the earth. So maybe I'd call that FME, the force on me due to the earth. To find the action reaction pair, you have to reverse those subscripts. So you'll say instead of FME, you're now going to say FEM. So the other side of the action reaction pair is the force on the earth as a result of me. And it means that, in fact, when I step off a curb, the earth pulls down on me with a force of 250 newtons, or excuse me, 250 pounds. And I, therefore, pull up on the earth with a force of 250 pounds. Okay. So hopefully that helps you piece it out a little bit and make some sense of what the third law means. I can tell you that it's part of the reason if you've ever tried to kill, for instance, a fly. Maybe you're sitting in a library or a bedroom or something, and you're trying to do your homework, and this fly keeps coming around and getting in your ear and your face and aggravating the heck out of you. We normally take a fly swatter and kill it or whatever. Some people are more peaceful than that and don't want to harm them. They try to let it go. I usually do that myself, even though mosquitoes and flies are a pain in my butt. But either way, if you've ever tried to smack one in the air, even though you know you can hit pretty hard, you'll hit a fly like that, and the fly will sort of fall off and then fly around like this, but they're fine. And you might be wondering, well, why is that? Well, Newton's third law can sort of help you with that because whatever force you hope to apply to that fly has to be able to apply that force to you as well. So if I wanted to put 1,000,000 pounds of force on a fly, that means the fly would have to apply 1,000,000 pounds of force to me, and that fly just can't do that. That's the short and easy way, and it in some sense helps people understand. But at the microscopic level or at the very high detail level, what I want you to think about is this. When I go to hit a fly, say, even if I'm like a professional baseball pitcher, maybe my hand can move at about 105 miles per hour. Okay. So if I take my hand and try to get it to move at 105 miles per hour to smack a fly, like you've seen on these smack competitions that you see on YouTube and whatnot, you could do that. You could actually swing your hand at 105 miles per hour and hit a fly, but it's not necessarily going to hurt the fly. And let me tell you why. Well, according to Newton's second law, the acceleration the fly is going to get is directly proportional to the force that you apply to them, and it's inversely proportional to the mass. But if you look at it another way and say the total force that you put on the fly is equal to the mass times the acceleration of the fly. So when I go to hit a fly, the fly, let's say, is sitting perfectly still. That's a simple case. You could actually assume the fly was flying the opposite direction, and that would apply more of a force to the fly. But let's just assume the fly is sitting perfectly still. And I come flying through with my hand at 105 miles per hour. And just at that instant, the fly touches my hand as my hand is moving at 105 miles per hour. So what's going to happen is that fly is going to compress my skin a little bit. His body's going to be compressed a little bit. And slowly, that compression is going to be enough force to bring that fly from 0 miles per hour up to 105 miles per hour. Okay. Because that mass of that fly is so small, it doesn't take a very large force to execute any acceleration because the force is proportional to the mass and is proportional to the acceleration. Since the mass is so small, we're talking on the order of a gram, which is on the order of a thousandth of a kilogram, which is what we're supposed to use in Newton's second law. Because of that, we get a mass that's going to decrease the acceleration by a factor of roughly 1,000, and therefore the force necessary to bring it from 0 to 105 miles per hour is very small, and that's why he is able to fly off. Maybe a little stunted, maybe a little stunned, but that's about it. The same thing's true if you try to hit a piece of tissue paper. Drop a piece of tissue paper in the air and try to hit it with all your might. And you'll see that because the tissue paper is so light, it takes almost nothing for it to be accelerated up to the speed of your hand. And the impact isn't that big of a deal when you initially hit it, just like it wasn't that big of a deal when you initially hit the fly either. So, hopefully, with those principles in mind and then working several examples, we'll be able to make some sense with it. So, I will point out that in chapter 4, the subsections are 4.1 force, 4.2 Newton's law, first law of motion, 4.3 is mass, and mass, by the way, is the SI measure of well, actually, it's just the measure of inertia. It didn't have to be that way. It also didn't have to be that way that the mass that we use in the equation for gravity is the same thing as the mass that we use when we're talking about inertia. But in both cases, we lucked out and it did. So the mass that we talk about, which is an object's reluctance to move, is its inertia, and it's measured in kilograms in the SI. In the CGS system, it's measured in grams. In the British system, which only us and like Myanmar use, the unit of mass is the slug. And you can see why we don't use that because no one wants to be quoted as a certain number of slugs of weight. Newton's fourth, or excuse me, section 4.4 is Newton's second law of motion. Section 4.5 is Newton's third law of motion. Section 4.6 is weight, the force of gravity, and the normal force. So we're going to talk about that. Section 4.7 is solving problems with Newton's laws, free body diagrams. Free body diagram is probably the single most important thing that you're getting out of this chapter, along with finding out how to calculate weight and how to calculate normal force. Those are the three biggest important, most important factors in this chapter. There's also two techniques that I'm going to teach you, maybe even three, that you're going to need, and those are super important. But all of that comes from chapter 4. And then finally, subsection 4.8 is problem solving, a general approach. Then we have, of course, the chapter opening questions, which you're always supposed to answer beforehand. We are studying dynamics. Remember, mechanics is broken up into kinematics, which is the study of motion without necessarily understanding how motion is caused, but understanding what the outcomes of motions are. And then there's the study of what causes the motions, what causes an object to accelerate, what causes an object to move at a certain velocity. That's the study of dynamics, and that's where we're getting at now. And I just want to point out that in order for us to do that, we have to have a concept of a force. A push or a pull, I said specifically here on page 2, a force is a vector quantity that can cause some object to accelerate. And I say some object because uh, if you choose a particular object, like let's say a car, a force is an object that can move a car. Well, there's a lot of forces in the world that aren't big enough to actually move a car. So I'm saying it can move some object. If you can find an object that it can move, then it qualifies as the object. It qualifies as an object that can be accelerated, and therefore that thing is a force. So a vector quantity that can cause some object to accelerate, it is usually recognized as a push or pull. Okay, so that's what a force is, and we need to understand that. And that was the big thing that, even though Aristotle knew about forces, his idea was a lot different. He said that objects basically needed a sustaining force whenever violent motion was occurring. However, it didn't need it for natural motion, and the natural motion was all dependent on the 4/5 elements: earth, wind, air, and fire. The fifth element being the quintessence was the heavens. But anything made of earth, for instance, its natural place would be at the center of the spherical, pseudo-spherical earth. Okay. and therefore any object made of earth had a natural motion in which it tried to get to the center of the earth, and that motion just occurred on its own and didn't require a force. Any motion that you tried to make it do that wasn't going in the same direction as it trying to reach the center of the earth, that was called violent motion, and you had to have a sustaining force to make it happen. And that was Aristotelian thought, and it seems really stupid a lot of times, but every now and then I find myself and other students completely thinking Aristotelian like. So just keep in mind as you learn more about the Aristotelian ideas of science that they're a lot more reasonable than you think. So we've talked about force and then Newton's first law of motion. We talked about that. Let's work with an example here with Newton's, actually a conceptual example. It says conceptual example 4.1, Newton's first law. A school bus comes to a sudden stop and all of the backpacks on the floor start to slide forward. What force causes them to do that? So this is sort of a trick question in that they're asking you for the force that makes the book bags move to the front of the room. That's a very Aristotelian thought. What we learned from Galileo and later from Newton was that the school bus riding down the road at, say, 35 miles per hour is moving at 35 miles per hour, and everything in it, if it's sitting still with respect to the bus, which includes, book bags sitting on the floor and kids sitting on the seats, then those too are moving at 35 miles per hour. Therefore, when the bus driver hits the brakes and abruptly comes to a stop, the tendency of the book bags, unless there's a net force acting on the book bags, their tendency is to continue moving forward at 35 miles per hour. And of course, they would come flying forward at 35 miles per hour. But as luck would have it, there is some friction force between the floor and the book bag. And that friction force, if it was big enough, it would keep the book bags from moving. But since it's not big enough, all it can do is make them go a little slower. So the book bags maybe come up at, 18 miles per hour instead of 35 miles per hour. So that's really the answer to why did the book bags shoot to the front. It's Newton's first law of motion or Galileo's law of inertia, saying that the inertia of the book bags requires them to try to maintain 35 mile per hour speed, and it's only external forces acting on it that aren't compensated for that makes it do less than that. So any questions on that one? Another thing that has to come into play, and you'll see this right after this example, conceptual example that I just worked, was inertial reference frames. So when we're solving physics problems, we need to use what we call inertial reference frames. In other words, we need to think of a coordinate system or some reference frame, some piece of the world that you're measuring heights and distances and velocities relative to. That should be what we call an inertial reference frame. And we define an inertial reference frame as a reference frame in which Galileo's law of inertia is not violated. So, for instance, if you took those merry-go-rounds that you see in playgrounds and stuff like that, the ones that you can sort of run beside and then jump on real fast and they'll spin really, really fast. If you imagine mounting a video camera above one of those right over the center so that you can only see the disc of the merry-go-round, and then you place a basketball dead center in the center of that disc, because the camera is only set up to see the disc itself instead of outside, you cannot really tell from the camera view whether the disc is rotating or not. And if you looked at it and watched that ball, chances are that ball, which was sitting really close to dead center, is still going to eventually shoot out of the screen. The reason why it's shooting out of the screen is because it tilted just a little bit, got a little bit off center, and because of that, its inertia, which was tending to make it go around and around like this, its inertia made it continue off in a straight line, just like the backpacks continued off in a straight line when the bus driver hit the brakes. Now, from the perspective of the camera, you would see a ball sitting there perfectly still and you wouldn't see anything touch it. All of a sudden, it would start accelerating out of the frame of the video. So, since you don't see any force causing that, it seems that Newton's first law of motion or Galileo's law of inertia was just violated. Therefore, that reference frame is not an inertial reference frame. Now, if you actually wanted to do physics with respect to that reference frame, it may or may not be good enough as an inertial reference frame. It all depends on, how many decimal places you need to have your velocities and positions and stuff like that. And it might be such a small motion that it doesn't matter. For instance, the Earth, we know for a fact, is rotating on its axis. And then in addition to that, the Earth is orbiting around the sun. And these are on the orders of thousands of miles per second. Now, it turns out most of the time when we do physics experiments, we can do them attached to the surface of the Earth, even though we know well that the surface of the Earth is actually in an accelerating state. It's rotating around its axis, and therefore its velocity is constantly changing at each point, and that is an accelerated reference frame. It's a non-inertial reference frame. But as luck would have it, that motion is so minor, you oftentimes can use it anyways and not detect any problems. Okay. You can see some, for instance, if you go to Smithsonian, you'll see the Foucault's pendulum. And if you watch that Foucault pendulum long enough, you'll see that the pendulum's just swinging back and forth like this. But if you come back an hour later, you'll see that now it's swinging back and forth like this. And that's because from that perspective, the pendulum is tending to maintain its orbit, its oscillations in one plane while the Earth rotates under it. So it looks like it's going just back and forth in one plane, and it is, but the Earth is rotating under it, so it makes it look like it's going through a bunch of different planes. So that's how we can define reference frames. I will say that Einstein used that to introduce his special theory of relativity without complicating the issue of with gravity. Because from his perspective, if you look at, for instance, planet Mercury, you would look at it from a sky view where you can see the sun and you can see the orbit of Mercury, and you'd say, wow, that's interesting. Mercury seems to be going in what looks like a very circular orbit. In order to do that, its velocity direction must change each instant, therefore, it's accelerating. Well, if it's accelerating, then there must be some force acting on it, but you don't see any forces. And since you don't see any forces, you would say, oh, this must be violating Galileo's law of inertia or Newton's first law of motion. Therefore, we're in a non inertial reference frame. And that's what Einstein did. Einstein said the laws of physics are the same for all inertial observers, and that was special relativity. Later on, when he does general relativity, he takes out the word inertia and he says the laws of physics are the same for all observers, because now he's conquered the idea of gravity, recognizing that it is not a force, but rather a puckering of space-time. So, all right, now that we've done that, we've talked about inertial reference frames, which is what's necessary for us to apply Newton's second law and stuff of that sort. What we haven't talked about is mass, and as I said, mass is the measure of an object's inertia. Your book says it's a quantity of matter, which I've always hated that definition because it doesn't really make any sense what you mean by matter. So more precisely, we can say that mass is a measure of the inertia of an object. The more mass an object has, the greater the force needed to give it to get a particular acceleration. That's what it is. The key thing I want you to know about mass is both mass and weight mean different things. So mass and weight. So in the SI system, the System International, mass is measured in kilograms. In the CGS system, mass is measured in grams. And in the British system, which is the one, like I said, us in Myanmar uses, mass is measured in slugs. Okay. Weight, on the other hand, is a force, which is a vector quantity in general, but it's, mass is clearly a scalar. Now, in the SI system, the unit of weight is the Newton, and 1 Newton is equal to 1 kilogram times meter per second squared, which if you look at Newton's second law, like I did a second ago, you'd see that M times A would have units of kilograms times meter per second, and that's exactly what that is. The CGS system has a unit called the dyne, which I think is just capital D, but I've also seen people put a DY, and that is one dyne is equal to 1 gram centimeter per second squared. And then in the British system, the unit of weight is the pound, which a lot of us are using the pound symbol nowadays. And technically, that is the slug. Well, let me write it this way: 1 pound is equal to one slug times a foot per second. So that's what the actual units are. And I'll give you a formula later for figuring out what the weight is, but I need you to understand that these are different. I also want to express to you that 1 pound is approximately 4.45 newtons, or another way of saying that is 1 newton is approximately 0.228 pounds, a little bit smaller than a quarter pound. A dyne is like 10 to the negative fifth newtons. So a dyne is a really, really small quantity. So when you have something in dynes, they often have values like 10 to the sixth or 10 to the 12th or something like that. I think that's enough for right now, as far as those things go. But now I've gotten the difference between mass and weight. Specifically, I said was a force, but it's specifically the force of gravity. It's the affinity that a particular heavenly body has on a particular object. In reality, though, gravity acts. According to Newton's law of gravity, it acts on any two objects that have mass. So if two objects have mass, then they're going to be attracted to each other, albeit very small amount of attraction. The force is really, 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 really small. The force of gravity is the weakest of the forces, and it is teeny. Okay, but it is a real force if you have a mass of any sort. So that's really what the force of gravity is. Now, when you're talking about the weight of an object, you're saying what kind of attraction does that planet that object's on have for it? Or if that object's not on the planet, then it's that force of attraction that it has, that the moon has on it, if it's on a moon. If it's on an asteroid or a comet, it's the same thing. It's the force of attraction that the comet or the asteroid has on the object. If you're actually on a comet, but you're actually near a planet, the planet might have a stronger pull of gravity on you than the local asteroid does. Then you have to figure out, okay, I'm going to call my weight, the force of attraction that the planet has for me, not the force of attraction that the asteroid has for me. Okay. So hopefully that clears that up a little bit and gets some things straight. Now I'm going to move on to an example in Newton's second law. Uh, on page, I don't even know what page, roughly page 90, you'll see these conversion factors that I just mentioned. Oh, one slug is about 14.6 pounds. Point six, oh, excuse me, 14.6 kilograms. Excuse me. I said pounds. I don't know why I even said pounds, but one slug is about 14.6 kilograms. There's technically no way, even though you've probably been to a doctor's office and heard people convert pounds to kilograms. You can do that, but what you're doing is you're going on the assumption that the pound was measured at basically sea level on planet Earth, and therefore was accompanied by a gravitational acceleration of 9.80 meters per second every second. When in fact, the gravitational acceleration at the bottom of Marianas Trench might be 1% smaller, and at the top of Mount Everest would be 1% larger. And if you go higher than Mount Everest, it's going to be even smaller, and so on and so forth. So when they say 1 kilogram is equal to 2.2 pounds, they're saying that that's equivalent to it at sea level. It's technically there's no way you can convert kilograms to pounds uh, as a conversion factor. There is a way, a formula that you use to calculate weight from mass, and that's all there is. When you go to calculate, when you go to convert, you're not technically converting units. You're doing some cheating stuff. Okay. All right, so let's look at example 4.2, which is an estimate example. Example 4.2. It says force to accelerate a car, and it says estimate the net force needed to accelerate. So A, we want the net force, and I didn't put a vector symbol on it because we're just imagining this going on in one dimension. So really, we're just going to assume we're trying to accelerate, in this case, a car and an apple in the same direction of the force. But what they ask for, they want to know what is the net force required to accelerate a car whose mass is 1,000 kilograms at an acceleration equal to 1/2 g. Now, watch out when you see 1/2 g, you might think 1/2 a gram, but gram is a unit of mass and therefore not a unit of acceleration. So, what they really mean is 1/2 of g, which is 9.80 meters per second every second. And of course, half of that is clearly 4.90 meters per second because half of 9 is 4.5, half of zero point 0.8 is 0.4, zero point 4 plus 4.5 is 4.9. So that's what we're asked in part A. And then part B, they ask for the same thing. What is the net force required to accelerate a 200-gram apple? So the mass of the apple is 200 grams, which equals 0.200 kilograms, and we want that accelerated at A equals 1/2 g, which equals 4.90 meters per second every second. So that's what we're asked to do in this problem, and now we're going to do it. Now remember, this is a estimate, so they're really expecting us to do one sig fig order of magnitude type calculation. I'm just going to work it like normal. So solution. The equation we'll need is Newton's second law, which says the summation of the forces is equal to mass times acceleration. We're reverting to one dimensional, so I'm going to say the summation of the forces in the x direction is equal to mass times acceleration in the x direction. And that's the only direction we're doing, so I don't even have to put the subscripts on there. But with that, I can say the total force required for part A is 1,000 kilograms times the acceleration, which is 4.90 meters per second, like that. And you can see that that is 4,900, and the units come out to be kilograms times meters per second. And technically, we only have, well, your author says repeatedly that this 1,000 kilograms has an ambiguous number of sig figs, and that's the answer if you ever get such a multiple choice question on one of your tests. The number 1,000 or the number 50,000 or the number 200 have an ambiguous number of sig figs. If I took the time to write 1,000 with a decimal point after it, then it would have 4 sig figs. But this in mind, we're going to say that this is essentially 5,000, and kilogram meter per second squared is a Newton. So we're going to say the net force required to accelerate a 1,000 car is about 5,000 newtons. Okay. And it was technically 4,900, but again, we only had maybe one sig fig. So that's how that worked out. Now I want to do part B, which is finding the exact same thing, but for a 200-gram apple. And in that case, it'd be 0.200 kilograms times 4.90 meters per second every second. Now, if I took 4.90 and divided it by 10, which is what zero point 0.2 means, that's 2 over 10, then that'd be 0.49. And then if I multiplied that by 2, that would be 0.98. So the actual force is 0.980. And again, that is kilograms times meters per second squared. And of course, that's about 1.0 newtons. So the force required to lift a 200-gram apple or to accelerate a 200-gram apple at half of g is about 1 newton. That's kind of handy. I'll also tell you that later on we're going to learn the unit of a joule, which is a unit of energy, and that's about the amount of energy that's required to lift a 200-gram apple from the ground up to a tabletop. So that might come in handy later as well. Anybody have any questions on that one? Okay, now we're going to do example 4.3, and this one says force to stop a car. What average net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? So what they want to know is what force, so I'm going to say the summation of the forces is equal question mark. Now, technically, I keep solving for the total force, and it's right to do the total force, but remember, it's really just one force that's required, and you could just call it F in that case. It's just a matter of I want you to always think of Newton's second law as the left-hand side is the sum of all the forces acting on the system that you said had a mass m and will experience an acceleration a. So just keep that in mind. It's perfectly fine to call that F on occasion, but remember Newton's second law should always be on the left-hand side, the sum of all the forces. Now, in this case, they're saying the mass of the car is 1,500 kilograms. So we can at least assume that has two sig figs. And we're wanting to speed it up from rest. So V initial is equal to 0 meters per second. What net average force is required to bring a car, oh, excuse me, to bring a car to rest? So that's my final velocity. So let me get rid of that I down there at the bottom. And I'm going to say the final velocity is 0 meters per second. And the initial velocity is 100 kilometers per hour. And of course, to convert that to meters per second, you divide it by 3.6 because it's 1,000 meters in a kilometer and 3,600 seconds in an hour. And if I do divide this 100 by 3.6, I get 27.78 meters per second. And obviously, we have really one, two, or three sig figs. I'm going to pretend like we have two because we had two on the others. So I'd call that 27.78, but the 7 and 8 maybe are not significant. Now, the other thing is we're trying to do this in a distance, which I'm going to refer to as delta x, because delta x is often x final minus x initial. And in this case, that's supposed to be 55 meters. So they want to know what force is required to stop such a car that's moving at 27.78 meters per second, and I want to stop it in a distance as small as 55 meters. To do that, we need some equations. So obviously, one equation we'll need is Newton's second law. So the summation of the forces is equal to mass times acceleration. So if we knew the acceleration, then we could calculate the force, and that's what we're wanting. So that's why I wrote that equation down. Now, I also need some way of calculating the acceleration, but I have a velocity initial and I have a velocity final, and I have a distance, not a time. So, v equals v0 plus at is not going to get it because I don't have the time. I could assume it's a constant acceleration and then say, well, the average velocity is half of 27.78. And then I could see how long it would take at that average velocity. And then I could use that other equation. But that introduces two equations. So we're going to go ahead and use the equation that I told you that some physics instructors don't allow you to use. Specifically, we're going to use v squared is equal to v0 squared plus 2a x minus x0, and I want to remind you that this x minus x0 is exactly the delta x that we're talking about. So to solve this, I'm first going to use the v squared equation to find out the acceleration, and then I'm going to plug that acceleration into the F equals ma to get the force. Your book is making a point to get the acceleration to be a negative and then say the force is a negative. I don't normally care too much about that. I think it's pretty obvious that that if you're slowing the object down, you're going to have to apply a force in the opposite direction of its motion. And that is normally, since we're calling the velocity a positive quantity, that would normally suggest a negative quantity for the acceleration, and therefore the force should point in the negative direction as well. That's certainly fine. I don't need a negative sign to do that. So unless I explicitly ask you for the direction or the sign, then you can sometimes just give me the magnitude. So starting with v squared equals v0 squared plus 2a parenthesis x minus x0, I can solve that for a to find that a is going to be equal to v squared minus v0 squared over 2 delta x. And of course, v final is 0 squared minus v initial, which is 27.78 meters per second quantity squared. And all that's going to be divided by 2 times 55 meters. So if I took 27.78 and I squared that, I would get 717 point, or excuse me, 771.7 negative. And then if I took that and divided by 2 times 55, I'm going to say that number divided by parentheses 2 times 55 close parentheses. And this gives me negative 7.016 meters. Notice the square of meters per second is meters squared per second squared, but then I'm dividing that by meters, so that gives you just meters per second squared or meters per second. So that's the exact acceleration that we get, and I should write the 1 and the 6 are not sig figs. So notice it did come out negative. This is why if you stuck the negative in F equals ma, then the F is going to come out negative. So I'll go ahead and show you just like the book did. I'm just telling you that in future I might not do that. I might just take the magnitude. Now the summation of the forces, which I've reduced to one dimension instead of talking about the vector quantity, is equal to mass times acceleration. So in this case, it's 1,500 kilograms times negative 7.016 meters per second per second. So times 1,500 gives me 1,052, and that's kilogram meters per second squared, which is a Newton, and of course it comes out negative. So the force is got to be in the negative direction, and it's going to be about 1,000 newtons. Just remember the negative is telling you, hey, you called the initial velocity 27.78 meters per second positive. That meant the car was going in the positive direction, and the acceleration came out negative, and the force came out negative. So that means the force has to act in the opposite direction that the car was initially going. That's the linkage between the two. If I had called the 27.78 negative, then I would have gotten a positive acceleration possibly, and the positive acceleration would then result in a positive force, and then that would suggest that you'd have to push, since the velocity was in the negative direction, you'd have to push on the car in the opposite direction the car was going, again slowing it down. So that's how that works out with regards to signs. Anybody have any questions on that? Now, I probably should have rounded that to 1100. Either one of those is acceptable, but let me just do that just for the heck of it. Your book did say it was 1100, so it really is more correct to call that 1100 newtons. And again, that's just because the 5 should have made the 0 round up as opposed to down. All right, so there's a couple of examples. Now we're talking about Newton's third law. If you're following the text, we would be jumping into the Newton's third law section, and I'm going to answer this conceptual question, which you notice when I do conceptual questions, I usually don't write them down or any solutions. So I'm going to do the same thing here. And it says, conceptual example 4.4, what exerts the force to move a car? And what they're asking is what makes a car go forward. So it's kind of complicated to explain this, and it's a little bit, or actually, it's a lot more involved than you might have considered. So it's really important for me to explain this to you. Your book has a paragraph they've written to explain it, and that's a good paragraph as well. But I'm going to explain it now, and you can rewind this over and over again to listen to it. The main thing is this is what's going on. When you go to take off in your car, let's say your car is parked in the middle or sitting in the middle of the road, it's in drive, and you push down the accelerator. By pushing down the accelerator, you're telling the engine system to flood more gas into the piston chambers. That more gas into the piston chambers is also going to make the piston chambers explode more rapidly, specifically blowing up the gas. And then when that gas explodes, that's going to push the piston head down through that force stroke and or through that thrust stroke, if you will. And then that's going to turn a shaft that's going to ultimately go through your transmission. Your transmission is going to have a bunch of sort of gears that change the rotation rate of the engine to match a little closer to the rotation rate that you need at the rear axle. So out of the transmission comes a drive shaft that's going to rotate at some new rate associated with this new pedal position that you have for the accelerator. Then that drive shaft is going into a differential. That's the big hog's head looking thing between the axles in the rear or in the front of the car, depending on whether it's front wheel drive or rear wheel drive. And it's called a differential because it turns out that when you make a turn around a curve, the inside tire, the tire closest to the center of the turn, has to go slower than the outside tire. And the only way to work that out is you have to turn those two wheels at a different rate, and that's what the differential does. Okay. Now that differential is going to change the rate of that drive shaft rotation as well. In fact, you can look up, rear ends have certain ratios, 12 to 1, stuff like that, 24 to 1, all sorts of ratios. I don't know where those numbers came from. I remembered looking that up sometime, and I might even be misremembering, but there is a different rate for your rear end. And of course, if you have a really high rate, you don't necessarily have much power, but you have a lot of speed. If you have a low ratio, then you have a lot of power, but not a lot of speed. But again, it's another ratio that changes the rotation rate of the drive shaft to make it the rotation rate of the axle. Assuming we're going straight, then both axles are turning at the same rate. Now, as those axles try to turn, they're attached to wheels, and the wheels are going to try to turn forward like that. Well, if the friction force in the ground is sufficient to keep those from just spinning willy-nilly, then the car can take off. But if the friction force is insufficient, then the car is going to spin out, which is what they do with dragsters and funny cars and stuff like that just before they do races. So what's going on there is you've added more gas to the engine to make the rotation rate of all that stuff higher, all in an attempt to rotate the wheels forward in hopes that the friction force will be so big that it doesn't allow the wheels to turn willy-nilly. So the friction force is going to push forward on the wheel according to Newton's third law with exactly the same magnitude of force that the tire was trying to apply to the ground. So the transmission and engine and all that stuff sent a command and actual force and torque to the rear axles to try to make the tires turn at a certain rate. And so doing made them apply force to the ground between from the tire to the actual road or whatever you're on. And if that friction force was sufficient, then that friction force will apply the exact same force in the opposite direction. And it's that friction force between the road and the tire that makes your car go forward. That's the weird thing. It's really the earth and the friction between your tire and the road that makes your car go forward. And not only that, that shows you that you can't do much with Newton's second law unless you also have Newton's third law, because even if you knew everything about your car, how much force it produces, how much torque it produces, what it weighs, you still couldn't calculate the acceleration of your car, because you need to know the force that the ground applies to the car, not the force that the car applies to the ground. So hopefully that helps you. And they do another one just like it in a second. So let me show you that one. This is example 4-5, conceptual example again, and it's called third law clarification. Michelangelo's assistant has been assigned to the task of moving a block of marble using a sled. He says to his boss, when I exert a force on the sled exerts an equal and opposite force backward. So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force, so the net force must be zero. I'll never be able to move this load. Is he correct? Okay, this is actually very much an example that I used to tell my students all the time before I'd even read this one. But it's really important because it helps you understand the difference between action reaction pairs in Newton's third law. Specifically, when he says, when I exert a forward force on the sled exerts an equal and opposite force backwards. He's stating Newton's third law, but he's left off a critical aspect. Remember, I said action reaction pairs happen when you reverse the subscripts. So right here, we're saying the force on the sled due to the assistant. So that's FSA. And then he's talking about the force on the assistant as a result of the sled. That's FAS. But the important point is the two objects or the two forces are acting on different things. So there's no way that you'd ever have two parts of an action reaction pair both in the left hand side of Newton's second law, because Newton's second law is the summation of the forces acting on an object or a system of mass m is equal to the product of that mass m and the acceleration that is its result. So when I talk about the force that the assistant applies to the sled, that is the force that goes on the left-hand side and can account for an acceleration. When I talk about the force that the sled puts on the assistant, that's the force on the assistant. It shouldn't be on the left-hand side of F equals ma for the sled or the stone. Okay, so hopefully that helps you. Anybody have any questions on that? All right, now I'm going to use Newton's second law and your knowledge of uh, projectile motion and free fall to derive a formula for weight. So here we go. Remember with free fall. So consider a mass m in free fall. So the mass m is right here. And when we studied free fall, we found that Galileo told us all objects fall at the same rate, independent of their mass, unlike Aristotle, who said that, if an object weighs 200 pounds and another object weighs 100 pounds, then the velocity of the 200-pound object will be twice as big as the velocity of the 100-pound object. That turns out to be completely wrong. F equals ma tells us why once we learn about weight and gravity. But the main thing is when we're studying free fall motion, we know that the acceleration due to gravity is the 9.8 meters per second every second downward. Okay. And we also know that in free fall, we're ignoring all other forces. So literally the only force acting on this mass is the force that we call the weight. So I'm pointing out to you, hey, this word you've been using all your life, weight, is actually the force of gravity. And you've got to remember that from here on out. The force of gravity is called the object's weight. Okay. So the force acting on the mass m is one force and only one force. That's the weight. But we also know that Newton's second law says the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And I might wish, for instance, to call the positive y direction downward, in which case maybe the x is to the left or something. Okay. So we know for a fact that the left-hand side of this equation is just the weight, W. Now, we also know from studying free fall that the acceleration on the left-hand side, since I pointed y downward, it's positive g. So the acceleration is going to be just plain g. Oops, I meant to write that in red so I'd be consistent with what I had here. Oops, I still meant to write that in red and it still didn't. Okay, so like that. So now, with this in mind, we can write the summation of the forces is just W, and that's equal to M times G. And guess what? That is the formula for weight. This is how we calculate weight. Okay. Weight is the mass of the object multiplied by the gravitational acceleration for that particular planet or wherever you're at. If you're on planet Earth, even if you go down as low as the bottom of the Marianas Trench or as high as Mount Everest, we know that the swing and the value of G is only going to be about 1% off. So it's just your mass times 9.8 meters per second gives you a really good estimate of what your weight is. No matter if you're at the bottom of the Marianas Trench or the top of Mount Everest. If you go deeper towards the center of the Earth, it's going to get a larger force. And if you go higher than Mount Everest, it's going to get a smaller force. But the main thing is, it's always mass times whatever G is at that location. Anybody have any questions for that? Okay. Now that we have that, I want you to think about your book, for instance, has a bust of Abraham Lincoln. So here's our bust of Abraham Lincoln. And Abraham Lincoln, of course, has a cool beard, so I'm going to give him a cool beard. He's got a cool mustache, of course. And I'm giving him some big googly eyes for no particular reason, but because I can't draw that well. And I'm going to hate him because he has a nice head of hair, which I don't have, and that upsets me. So I'm going to do that. So there is a bust of Newton. And of course, this bust of Newton is sitting on a tabletop. And we don't really think of tabletops as animated objects, so we don't really think of them as applying forces to things and stuff like this. So that might seem a little weird to you, but it has to be, okay? So I'm going to apply Newton's first law of motion here. When I see a bust of uh, Abraham Lincoln sitting on a tabletop, I can think of Newton's first law, which says an object in motion tends to stay in that state of motion unless acted upon by a net external force. This object is not moving, so the bust is not moving, and it is still not moving. Now, if the object wasn't moving, it could be, for instance, like a mass on the spring. If you actually look at a mass on the spring at a particular instant, it might be at the point where it's completely come to a stop. But if you watch a split second later, you'll see that it's moving downward with some velocity. Or if you watched a split second earlier, you see it's moving up. So you got to make sure you're not making that mistake. But since I see the bust is not moving and it's still not moving, therefore the acceleration of the bust is equal to zero. We know the velocity is zero, but the velocity is still zero, and the velocity is still zero, and the acceleration is given by the change in velocity, which is zero, divided by the time taken, which could be anything. So we get the acceleration is zero. Since the acceleration is zero, we know, therefore, the net force on it is zero. Okay? Now here's the other part. We know at least one force is acting on it because there's a force called weight. Specifically, the free body diagram for this object would look like this. Here's the mass of the bust. We have acting on it a force that's called the weight, which equals m bust times g. So we know that force is acting on it, yet we see that it's not accelerating. So according to Newton's first law of motion, then there must be at least one other force acting on it. I would say. But we know gravity acts on the bust. Because of that, there must be at least one other force that is canceling the gravity force. Okay. So, using that logic, we've now reached the conclusion that there's another force on there. And in fact, that other force is a force that we call the normal force. And it's called normal because geometrically speaking, a vector or an arrow or something like that that's perpendicular to a surface is said to be normal to the surface, not perpendicular. There's actually more specific definitions to things like normal, perpendicular, orthogonal, things like that. And using the word normal is more correct when we're referencing one line being perpendicular to a surface, or when we say two lines are perpendicular to each other, that's more reasonable. But when you're saying a line is perpendicular to a surface, you're supposed to say normal, and that's what it means. Now, this one has to be normal because if it, for instance, pointed to the left a little bit, or to the right a little bit, or out of the page a little bit, or into the page a little bit, that would tend to cause Newton's, or excuse me, that would tend to cause Abraham Lincoln's bust to move forward into the page, or outward out of the page, or left or right, whichever direction that force had other than normal would tend to cause motion. And that would be the table acting like it's animated, like it has some kind of soul or thinking brain or something like that. So in fact, the normal force is a force that a object, a horizontal surface or something holding up another object, exerts on things. And if it bothers you about thinking about this inanimate object applying a force or something, think of it more like a elephant. If an elephant walked up and sat on that table, you know for a fact the table couldn't hold the whole elephant and the table would just collapse. It's not that the table is actively thinking about applying a force. It's that the design of the table is such that it has a horizontal surface that can sustain a certain amount of force before it fails. And that force is the normal force. And it happens to be the force that we use in engineering if we want to calculate what kind of joist we need for a floor, or what size rafter we need for a roof, or what size joist we need for a ceiling, stuff like that. All of those are the normal forces that those members, those 2x6s, 2x8s, 2x12s, flitch plates, and all that stuff, that's the force that they have to supply. So that's our normal force. Now that we have that, let me give you an idea of how you go about figuring out exactly what the normal force is, because that's something that's going to happen over and over again this semester. So I'm going to do example 4.6. And example 4.6 says, weight, normal force in the box. A friend has given you a special gift, a box of mass 10.0 kilograms with a mystery surprise inside. The box is resting on a smooth, frictionless horizontal surface of a table. A, determine the weight of the box and the normal force exerted on it by the table. B, now your friend pushes down on the box with a force of 40 newtons, as in figure 415b. Again, determine the normal force exerted on the box by the table. And then C, if your friend instead pulls upward on the box with a force of 40 newtons, see figure 415C, what now is the normal force exerted on the box by the table? So that's what we're talking about. I do have a mass given by 10.0 kilograms. I have a force that's going to be 40.0 newtons, and that's going to be up in one case, or actually, it's first going to be down, or first it'll be none for part A, and then for part B, it's going to be down, and then for part C, it's going to be up. And I'll call that F sub P for the force that the person is applying. So now I'm going to draw a coordinate system. This is something you want to get used to doing as well. It is helpful to have a coordinate system, and once you have a coordinate system, then that allows you to decide which directions are positive, which directions are negative, which directions are X, and which directions are Y. I normally try to call Y upward, the positive Y direction upward, the positive X direction to the right, but sometimes I reverse those. Okay. So the way we draw a free body diagram is we treat the box in this case as a point object. When we get to the point where we're studying torque and center of mass, we can start treating objects as if they have a physical size, but right now we have to pretend like they're point particles. So this is the mass of 10.0 kilograms. And now on this coordinate system, we need to draw the forces acting on it. I tend to draw forces pointing in the negative direction red and forces pointing in the positive direction green. And if they're not pointing in either axis direction, I just use some random color. So right now I know that the weight this thing has, W, is equal to mg, and that therefore it's 98.0 newtons is the weight acting on it. And this is really part A. So, in addition to that, we know since it's sitting on a table, we just learned that evidently that requires there to be a normal force. That normal force is acting in the upward direction. So I'll draw it right here and I'll just subscript it, or I'll call it F sub n. Now it is technically a vector, so I could put a vector symbol over it just like I could put a vector symbol over the W as well, but sometimes we leave those off in the free body diagram. Now what we do is we apply Newton's second law. Newton's second law says the summation of the forces is equal to mass times acceleration, but this is a two-dimensional problem, so I'm going to reduce that to the summation of the forces in the x direction equals mass times acceleration in the x direction, and the summation of the forces in the y direction equals mass times acceleration in the y direction. Now, in this case, we see that no forces are acting in the x direction whatsoever, so I can say that's going to be zero, and therefore this is going to be zero. So we have no reason whatsoever to use F equals ma for the x direction. However, we are told that this box is just sitting on the table, so we know the acceleration is zero. So in this case, I can say, well, there's a force acting in the upward direction. That's a Fn. So I'm going to refer to that as a positive force. And then there's a force pointing in the downward direction. So I'm going to refer to that one as a negative. And remember, Newton's second law, the left-hand side, is a sum of the forces. It's not adding and subtracting the forces. You're only adding them. But in this case, the thing I'm adding is the weight, which points in the negative direction. So I write a negative symbol in front of it. And then that's equal to mass times a sub y. But as we said, the object's not moving, so the acceleration in the y direction is zero. Now, mathematically, adding a negative is the same thing as subtracting. So from here on out, I'm probably just going to write this left-hand side as F minus W instead of F plus the negative of W. You just need to remember that we're never subtracting forces on the left-hand side of Newton's law. We're always adding them. It's just sometimes their magnitudes are negative. And from this, what we've discovered is that the normal force is equal to the weight in magnitude, and therefore it's 98.0 newtons. So now I can say the normal force is 98.0 newtons, and I can say the weight is 98.0 newtons. Now for part B, I'll draw the coordinate system again, and I'll draw the mass again. And of course, this is our X direction, this is our Y direction. And this time we have the weight acting downward. W equals 98.0 newtons. But we have, in addition to that, a force acting upward, which is the normal force. That's the one we're looking for. But we also have another force acting downward because in part B it says your friend pushes down on the box with a force of 40 newtons. So since that's down, I made it red, and we're going to say FP is equal to 40.0 newtons. Now, again, the summation of the forces in the x direction is irrelevant, but the summation of the forces in the y direction equals mass times acceleration in the y direction. We're told that this guy's pushing down, and of course, if the table failed, then obviously the box would accelerate through it. But we're not learning anything like that, so or we've not been told anything like that. So we assume that the object's not accelerating, and in fact, the acceleration in the y direction will be equal to zero. So now what we have is the normal force is the positive one, and then we're subtracting from it the FP, which is 40 newtons, and because it was pointing down, that's why I'm subtracting it. And then the 98 newtons, which is the weight, that one's negative as well because that one was also pointing down. Now we can solve for the normal force, and because of that, we see that the normal force is 98.0 newtons plus 40.0 newtons, which equals 138.0 newtons. So that's what the normal force is in the second part. Anybody have any questions on that one? Now the same thing happens with C here. Again, we've got X, we've got Y, we've got M, we've got 98.0 newtons. We've got a normal force acting upward, but this time the person, the friend, is pulling up on it. So we have a second green force, and that is FP is equal to 40.0 newtons. And again, starting with the summation of the forces in the y direction equals mass times acceleration in the y direction. And we know that the object's going to stay still, so the acceleration should be equal to zero. Now, in this case, we've got two things that'll be positive and one thing that's negative. So we're going to say Fn plus 40.0 newtons minus 98.0 newtons is equal to zero. And from that, we get that Fn is 98.0 newtons minus 40.0 newtons, which equals 58.0 newtons. And now we've seen how we've learned how to calculate the normal force, which right now is not going to be that important, but by the time we get to the next chapter, it's going to be used a lot. Okay. It turns out that the friction force is directly proportional to the normal force, and it's going to get more complicated. These are all horizontal surfaces, and the only thing that made them change from being exactly equal to the weight was additional forces acting either downward or upward. And you could also have forces that act downward and to the left at the same time, in which case you have to break the forces down into components parallel to the x-axis and the y-axis, and the y ones are going to contribute to the normal force, but the x ones are not. So this is how you do it. This is how you determine the normal forces. Normally you have a summation of forces in the y direction or in the direction perpendicular to the surface. And if the acceleration in that direction is zero, then you can solve for the normal force, and it'll be somewhat related to the weight in some way or another. Okay. Any questions on that? All right. So now we're going to example 4.7. It says accelerating the box. What happens when a person pulls upward on the box of example 4.6c with a force equal to or greater than the box's weight? For example, let FP equal 100 newtons rather than the 40 newtons shown. So that's our example 4.7 or 4-7. Again, we have a mass that's equal to 10.0 kilograms. We have a normal force. Actually, I'm not going to write the normal force. What we're asked specifically is what happens when a person pulls upward on the box with a force equal to or greater than the object's weight. We do know the object's weight, W, is equal to mg, is equal to 98.0 newtons. And they're suggesting that the FP in one part, I'm actually treating this as a two-part question. They're saying what happens with the force equal to or greater than. So I'm first going to handle the equal to case, and then I'm going to handle the greater than case. So for part A, I'm going to say the force by the person is 98.0 newtons. And then for part B, I'm going to say the force by the person is 100 newtons. So here's my free body diagram again. X-axis to the right, y-axis up. Mass is a point particle, 10.0 kilograms, like that. I have a force acting downward. That is the weight, which equals 98.0 newtons. Now, in addition to that, I have a FP pointing upward. And I also have a normal force Fn. Now I'm going to say the summation of the forces in the y direction equals mass times acceleration in the y direction. In this case, I'm not really sure what's going to happen. I've not been told whether the box is going to lift off the table or anything like that. So I'm going to sort of play it by ear and find out what happens. So I'm going to take the forces that are acting on the right, and this is all part A, right? So I want you to remember this is part A where FP is equal to 98.0 newtons. Now, with that, I'm going to say that we have Fn plus 98.0 newtons, that's the FP, minus 98.0 newtons, that's the W, is equal to 10.0 kilograms times A. And I don't need to subscript that A because it's the only acceleration we have, so I'm just going to call it A. Now, in this case, what we see is the 98 that corresponds to FP and the 98 that corresponds to the weight are actually canceling one another out. One's positive, one's negative, so they're going to get zero. And at that point, we have Fn, the normal force, is equal to 10 kilograms times A. And it would be pretty crazy if you just laid something on the table and all of a sudden the table made it start accelerating. So we have to reach the conclusion that the F normal must equal 0 newtons. Or else it would be magic. And magic's not a thing in physics. Okay. Magic doesn't happen. So we don't have an inanimate object like a tabletop. It's not going to come along and just cause something to jump off of it. I mean, if someone kicks the table, then yeah, the normal force could make the thing on the table jump off of it because the table's been moved and stuff, but a normal table just sitting there is not going to happen. So what we've decided is that when the normal force, or excuse me, when the force that the person applies to it is equal to the actual weight, then it just cancels out the weight and it cancels out the need for the normal force so that the normal force is zero. In fact, if you were weighing the table when this happened and you slowly pulled up on it with a force of 40 newtons and then 41, 42, 43, 44, and you got up to slowly approach 98, the instant you got to 98, the table would be just its own weight, whereas before that, the table would have been the weight plus the normal force. So that's what would actually happen with this as we approach the 98 newtons. Now, in the case of the 100 newtons, it's all pretty much the same diagram, except now we have FP is equal to 100 newtons. We have F normal is that way, and we have the weight is 98.0 newtons downward. And again, we're going to take the summation forces in the y direction equals mass times acceleration in the y direction. In this case, we're going to say Fn plus 100.0 newtons minus 98.0 newtons is equal to 10.0 kilograms times A. Again, I'm not subscripting A for the same reasons. Now, in this case, we see that the 100 newtons is more than enough to hold up the weight. So it's going to completely take off the responsibility that the table has of holding the weight up. And therefore, we reach the conclusion that, again, Fn is equal to 0 newtons. Okay? Because of that, we end up getting 2.0 newtons is equal to 10.0 kilograms times A. So we learned that A is 0.20 meters per second. And the fact that it's positive tells us, oh, this force pulling up on it is going to cause this box to accelerate upward at a rate of 0.20 meters per second every second. And that's what happens. Anybody have any questions on that? All right. I'm trying to do a bunch of really straightforward, simple Newton second law examples. So 4.8 is the next one. And that is example 4.8. It says a 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g downward. She stands on a scale that reads in kilograms. A, during this acceleration, what is her weight and what does the scale read? And B, what does the scale read when the elevator descends at a constant speed of 2.0 meters per second? So what I have here is a mass is equal to 65 kilograms. We have an acceleration that is downward and it's 0.20 g, which equals 0.20 times 9.80 meters per second. Of course, dividing that by 10 would make it 0.98, and then multiplying that by 2 would make it 1.96 meters per second, and I'm going to say that that is downward. Okay, so we've got that, and that's for part A at least. And then for part B, V of the elevator, and I should say this is A of the elevator, V of the elevator is 2.0 meters per second downward again. Okay, draw my free body diagram. Actually, let me draw an elevator first so we can get some sense of what we're talking about here. So here's our elevator. This is a scale. This is the woman standing on the scale. Now I'm going to draw the free body diagram for the woman on the scale. Now, what we have here is a mass of 65 kilograms. And what we have acting on it is a weight. W equals mg. I think that's 687. Let's try 65 times 9.8. 637 is what it is equal to 637 newtons. That's one extra digit than is a real sig fig, so that's how that works. And now that's the weight of gravity pulling down on the girl. The other force acting on the woman, excuse me, is the force of the scale, and that's acting in the upward direction. So I'm going to draw it green, and that's F scale, which I'm also just going to call F sub S. Now, that scale is, or that force is what the scale is going to read, but the scale is going to read it in kilograms. And of course, what it's measuring is something like the weight. So the formula it's expecting is like M times G, and it's been calibrated so that you divide out the G. So whatever I get with that force of scale, I divide that by 9.8, and that'll give me what the scale reads in kilograms. Now, the other thing I have to point out here is that the acceleration is downward. So over here to the right of the free body diagram, I'm going to say A is equal to negative 1.96 meters per second. And the reason I said it's negative is because it points down and I chose up as the positive y direction. So now I've got to use my Newton's second law. The summation of the forces in the y direction is equal to mass times acceleration in the y direction. And the forces acting on it, of course, are F sub S, which acts in the upward direction, minus 637 newtons, which acts down. Remember, it's plus a negative, but I'm writing minus because it's easier to write that. And all of that is equal to m times a. Well, her mass is 65 kilograms, and her acceleration is actually negative 1.96 meters per second. The negative is absolutely necessary because that points in the direction, according to our coordinate system, that is the negative y direction. So the acceleration is actually in the negative y direction. To solve this equation for F sub S, I'm going to add 637 newtons to both sides. Now, 65 times 1.96 gives me 127.4. So this right hand side is supposed to be negative 127.4 newtons. And of course, we only had two sig figs, so the 7 and 4 are not significant figures. And we've already added 637 to both sides, so I just need to make sure we do it on this side as well. So now I'm going to get that the force that the scale is supplying is 637 minus 127.4. And that gives me 509.6 newtons. But again, the ones place and the tenths place are not sig figs, so I have to underline that. So that's the force that the scale is reading. The mass that the scale reads, which I'm also just going to call M sub S, is just the force that the scale reads, like I said, divided by G. So I'm going to take this 509.6 newtons and divide it by 9.80 meters per second. And that should give me kilograms. So when I divide 509.6 by 9.8, I get 52.0 kilograms, and that's the answer. So Just like you've probably experienced when you ride an elevator, when it first starts to accelerate downward, you feel a little bit lighter. It's like it's not affecting your knees. It's a little bit easier, and you maybe even feel like you can jump so high that you hit the ceiling. And I do this when, when my kids were little girls or were little girls, and I'd take them out to my college during the weekends or whatever, and we'd jump up and down in the elevator and show them neat tricks. And I could jump. All of a sudden, my head would touch the ceiling, and which I normally can't do because I'm short and I don't have that much skills in terms of jumping. But anyways, hopefully y'all can tie that to everyday life. Now that we've done part A, which is what we just did there, now we're going to do the same thing for part B. The only difference for part B, though, is that A is equal to 0, but V is equal to negative 2.0 meters per second. So, with that in mind, I'm going to write out Newton's second law again. The summation of the forces in the y direction equals mass times acceleration in the y direction. And that means the force on the scale minus 637 newtons is equal to 65 kilograms, but the acceleration is 0, so that right-hand side is 0, and therefore we get that the force of the scale is 637 newtons. That means the mass of the scale is the force of the scale divided by g, which means 637 newtons divided by 9.80 meters per second, which gives us, lo and behold, 65 kilograms. So there's no change in her apparent weight when she's riding on the elevator at a constant speed. But when it's accelerating upward, in that case, it would have been a positive, and you'd see that it would actually increase because you're adding the 637 to the m times a. If the m times a was positive, then it's going to get bigger than the 637, and then of course you end up getting a increased apparent weight because she's accelerating upward. And if you've ever ridden an elevator, when it first takes off in the upward direction, it is accelerating for a split second, and if you hold your knees kind of loose, you can feel it like it's squishing you down a little bit, and that's really what's happening. It's acting as if you have increased your apparent weight by a bit. Any questions on that one? All right, so we got a couple more problems I'd really like to get to, and we got about 14 minutes. So let's try example 4.9. Example 4.9 says adding force vectors. Calculate the sum of two forces exerted on the boat by workers A and B. So we have a pretty straightforward scenario here. I'm going to go ahead and draw the boat. So I'm going to say our boat looks like this. There's the keel. And I'm going to imagine a coordinate system. This is going to be my x-axis. This is going to be my y-axis. And what we have here is a force at 45 degrees. And this is called FA. And its magnitude is 40.0 newtons. And its angle is 45.0 degrees. And then there's another force. Notice I'm not drawing these forces green or red because they're not aligned to a particular axis. So I haven't broken them down into components yet. And that's a good reminder to say, hey, I should not be calling these red or green yet because I don't know what their X and Y components are. But there's the 37 degrees. And this is FB, whose magnitude is 30.0 newtons. And what they want to know is the summation of the forces is question mark. Okay. So what I need to do is decompose these vectors into components. So if I look at F sub A, if I try to travel from the tail of A to the head of A by going only parallel to axes, then I have to go from left to right on the horizontal axis, and that's the positive direction. And then I have to go from bottom to top parallel to the y-axis. So this is FA sub y, and that one down there is FA sub x. I can use my knowledge of trig to say that the cosine of 45.0 degrees is equal to adjacent over hypotenuse, and the adjacent is the one touching the angle, so that's FA sub x over 40.0 newtons. And I'm forcing the sign here, so FA sub x is equal to a positive 40.0 newtons times cosine 45 degrees. And that gives me, I think, a positive 28.28. Yeah, 28.28 newtons. And that's one extra sig fig, or one extra digit. And then the sine of 45.0 degrees is equal to opposite over hypotenuse, and the opposite is FA sub y. So FA sub y is also being forced to be positive, and that's going to be 40.0 newtons times the sine of 45.0 degrees. And of course, we know the sine and cosine of 45 are both the same, so this is going to be 28.28 positive newtons. Now I'm going to do the same thing for F sub b. And again, we see that the x component of F sub b is positive, and we also see that the y component is actually going to be negative, so that's F sub b sub y. Now I can say cosine of 37.0 degrees is equal to adjacent over hypotenuse, so that's FBX over 30.0 newtons, and that is FBX is a positive quantity, so I'm going to force that to be positive by writing a positive sign, and then times 30 newtons, and then times cosine 37.0 degrees. So 30 times cosine 37 gives me 23.96 newtons. And similarly, the sine of 37.0 degrees gives me opposite over adjacent, so that would be FB sub y over 30.0 newtons. Now this one is actually negative, and I've got to force it to be negative. So this is going to be negative 30.0 newtons times the sine of 37.0 degrees. So 30 times sine 37 is 18.05. So this becomes negative 18.05 newtons. Now remember, the resultant x component is FA sub x plus FB sub x. Of course, if we have more than two forces, we continue to add those forces and just say the x components, but that's all we have for this case. So in this case, I'm going to say FA sub x was in fact positive 28.28 newtons, plus FB sub x was 23.96 newtons, and 28.28 plus 23.96 gives me 52.24 newtons. Similarly, R sub y, the resultant of the two vectors, is FA sub y plus FA sub, or excuse me, plus FB sub y. Again, if we had more than two forces, I'd just keep adding terms. Now, FA sub y was positive 28.28 newtons, and FB sub y was negative 18. Whoa, Nelly. I accidentally, evidently started this making my lines correct, and it was or neat, and it's not doing a good job. Why does it keep jumping to that? Okay, so negative 18.05 newtons. So 28.28 minus 18.05 gives me 10.23 positive newtons. Now all I have to do is plot these components on a similar axis, meaning an axis that is parallel to the previous axes that I used. So for instance, my x-axis was pointing to the right and my y-axis was pointing up. So I'm doing that again. Now I realize my x component has to be 52.24. So, and that's a positive. So I'm just going to draw this to this distance, and that's 52.24 newtons. And that's supposed to be horizontal, even though it looks like it's not. And then the y component is vertical. And in this case, it's a small fraction of the other one. It's only about 10. So this is 10.23 newtons. And therefore, our resultant vector is this guy. And of course, that angle right there is theta. And I can compute R using the Pythagorean theorem. And that is 52.24 newtons squared plus 10.23 newtons squared. It turns out that when you multiply or when you square 52.24, which only has 3 sig figs, then that gives you 2,729. And since it only has 3 sig figs, it's only good to the tens, not tenths, tens place. And then the 10.23 squared, that gives you 104.7, but that's only good to 3 sig figs, so it's only good to the ones place. So when I add these two numbers, I can't have the tens place or anything smaller. So I'm adding 2729 to that, and I get the square root of 2,834 newtons squared. But as I said, the tens place, and actually I should do it like this. The 4 and the 0 are not sig figs. So now I take the square root of that, and I realize I only have 3 sig figs, so the answer is 53.23 with one extra digit. So it's just barely bigger than the x component, but it is a little bigger. And then tangent of theta is equal to adjacent over opposite. Excuse me, opposite over adjacent. So that's 10.23 newtons over 52.24 newtons. Therefore, theta is equal to the tangent inverse of 10.23 over 52.24 newtons. And if I do that, I take the inverse tangent of 10.23 divided by 52.24. And that gives me 11.08 degrees. So the resultant, which equals the sum of the forces, is equal to 53.23 newtons at 11.08 degrees. And that's it. That's the entirety of this problem. I'd like to have worked more, but I only have 2 minutes left and I can't afford that time. I don't know if I'm just going to start next time with the remaining examples or if I'm going to make a video in between. I know there's plenty of videos. I've even pointed them out and given them to you in this week's module. So by all means, you can get enough. I haven't decided yet. I might do some more examples next time from this chapter, or I might just jump into five. So I would recommend you guys go ahead and start looking at some of those examples that I do in the videos that I listed as optional videos for this week. But you guys are free to go. I'll wait for the last person to leave in case anybody has any questions. Don't forget to chat me your first and last name if you haven't done so already. And be prepared. I'm going to change some of the due dates for just the online test, not the face-to-face one, just because I like to do them every two chapters, and I like to have more than a couple of online tests before you take the next face-to-face. So just keep an eye on that. I'll make an announcement and send an email when I do it, but just know that the next online test is going to be on a different date than it says in their syllabus. Have a good one. Thanks, everybody.
Hi, I had a question.
Yes, Shania. How can I help
Um,
you?
on Thursday, is it okay to send you a message? So on Thursday, I have a graduation to attend at five
Yes.
o'clock. At four
Yes,
o'clock, I was
that's
gonna
not a
send you a
problem.
message about it.
Yeah, are you
Okay,
just gonna
thank
have to
you.
miss Thursday?
Yeah, I had to miss Thursday because the graduation's at like five.
No
Well, you got
problem.
to get there at three at five. Okay.
Yeah, it's not a problem. And I'm going to be doing the same lecture tomorrow night. So you can catch that one, or you can just wait for the other one to come up on Thursday night, or sometimes it doesn't come up till Friday. But either way, you can either catch the Wednesday one, or you can catch that one when it does come up.
Okay, like when you upload the video or
Yeah, yeah. My other 241 class is at the exact same place. So whatever I do tomorrow night, it'll be the same thing I'm doing Thursday night. So you can either,
okay.
try to attend if you want a real meeting, you can attend, or you can just wait for that video to come up, or you can just wait for the video for Thursday night to come up.
Okay, thank you.
You're welcome. Have a good one, Shania.
You did the same.
Zane, Jacob, Vincent, Cameron, anybody else have any questions?
Yeah, I have one question.
Yes, sir.
So for the exam or for the face-to-face that we just took,
Hmm.
um, I did not, I think I emailed you about this, but I did not submit my scrap paper, but
Yeah.
I did the exam. And you said that I might have to retake it. So
Yes.
yeah. So because I was looking when I was finished the exam and I didn't see where like I could like submit a screenshot or anything. Like I didn't see an option through my exam when I was in the lockdown browser. So
Right. So the instructions were what told you all that. So
mhm.
I have to just look at your video. It'll show me exactly what you saw on the screen and everything like that. And once I look through that, I'll decide on whether I can take it as is. But pretty much, if you didn't turn in your work and didn't show me your work, then you're not going to get any credit. The most you could get is even 50% for even getting all right answers. So that's the problem. I can't give a test and not have you show your work, but we'll check and see what it works out. It might be something where
Okay.
it's obvious, like if I can see on your work and stuff where you've done it, I might if I can get enough information on that to see that you did it or whatever,
Hmm.
then I might just be able to just count it and not worry about it. But I'll get back with you, and it's
Okay.
not disciplinary. You're not in trouble or anything like that. It's just a misunderstanding, and we'll fix it. Okay.
Okay. Am I able to email you this scrap paper? Because I still have it. Or would that not?
Yeah, it doesn't do me much good because I have to
Okay.
see it immediately when you did it in the
Yeah, that makes
confines
sense.
of the lockdown browser, and then I just use that video to verify it's the same sheet when you send it to me. So
Yeah. Okay.
remember in future ones, if we ever do one online like that, instead
Right.
of literally person to person, you've got to do that process. So,
Got it.
all
Okay.
right,
Thank you.
no
All
problem.
right.
See
You
you
have a good
soon.
one.
You too. Anybody else?
Yes, hi Professor. I wanted
Yes.
to ask about the lockdown browser
Hmm.
test. I made a huge mistake and I thought it was due at midnight on June 8th, and it was of course due at 2 a.m.
Hmm.
yesterday, and I missed that detail. I just wanted to ask if there's any possibility of reopening it and if I could take a penalty instead of a zero, because I completely understand that
Oh
the
my God.
deadline
So
was past.
what I did was I had to put it due at 2 a.m. or else it'll literally stop you taking it at 11:59. So that's why I had to put 2 a.m. the next day in case someone started at 11:59. I wanted to give them the ability to finish the test and have it still count. But if you started at like 11:50 and then 11:59 rolls around, it would just stop you right there and you'd basically only get whatever you'd done at that point. So for future reference, that's why I did that at 2 a.m. I haven't put out the solutions or anything. When can you take it if I open it back up for you?
Tonight.
Okay, that would be good. I'll open it back up and you get it tonight. Remember, you're going to have to take a photograph of each of your pages that you work. Just follow the instructions, and you got to email me the worked problems within 15 minutes after you submit the test. You not only have to
Okay.
show them to the camera while you're taking it at the end, but you also then have to send me those by email as a PDF immediately thereafter. So make sure you follow the instructions, and I'll go ahead and open it up. There'll be a penalty for getting the extra day, but it won't be a huge one. It'll like be 10 points off or something.
Okay, I really appreciate it. Thank
No
you.
problem. I'll work with you. And that's Cameron, right?
Yes.
Otherwise, I'll forget the name. And you are in this section,
Yes, I am.
NO2. Okay, no problem. I'll take care of it, sir. It should be done in about 5, 10 minutes.
All right. Thank
Good
you.
luck. You're welcome.
Have a good day.
You too. Vincent, Jacob, anybody else have any questions?
Yeah, can you hear me?
I can.
So when I took the exam, I didn't see anywhere where it said to email you my work. It had the picture afterwards, and I
hmm
showed it to the camera during the exam.
Yeah, you're going to
Um,
be in the same
but
problem as the other guy. Yeah, it says in the instructions that's what you have to do to get credit for it. So I'm going to have to
okay,
look at it, see what I got. I might be able to let it go this time, but probably not. So just be prepared and watch for an email from
okay,
me.
okay, because I thought it I didn't see where it said that, but I took the picture afterwards, and I thought I figured that picture was probably what was supposed to happen.
So you held up
So
your pages to the computer
yeah,
monitor
yeah,
and you videoed all the pages.
yeah. It was only like the front and back of one page. So I held it up to the camera during the exam because that's
Uh-huh.
what I didn't see anywhere where it said while I was taking
Gotcha.
it. And then afterwards, it had also to take a picture of both sides.
Right.
But I just didn't see the email part of that. So
Okay.
I've
Well,
had
if
it
you
shown
showed
to
it to
you.
me and I can see it, then it's not even going to matter. It's just a pain for me to look at it that way as opposed to having it in my
Yeah,
email. That's what I
yeah,
was
that's what I
hoping would
was
happen with the
thinking
other guy.
about. I can still send it to you with better quality on the email, and then you can,
I
I
can't
guess,
take it
cross
now
reference
just
it.
because there's no way of me verifying that it looked exactly like what you showed me on the video. So if I saw the
Okay,
video and it was clear enough and then you could send me a copy, then I could take it, but I have to first see the video. So just keep an eye on that and we'll see it. But just remember, that's the way it works. If you're taking a quote unquote proctored test without a physical proctor, then I have to see your work in real time while you've been locked down under that camera situation. And then I have to have a copy that's cleaner and easier for me to read within 15 minutes. And the reason why it's within 15 minutes is because you could go and say, oh, well, I screwed up this problem. Let me rework it and do it right. And I have to compare that to the one you showed me in real time to make sure you haven't altered your solution. So
yeah,
just
okay.
for future, just make sure you know that, and you should be fine. We'll work it out. It's not a big deal.
Okay. Yeah, I tried to have it be a good picture for the lockdown browser because
Mhm.
I figured the quality might not be
Yeah, that's always
the
a danger.
best, but
Hopefully that'll work.
hearing you, yeah, hearing you talk about the email as well, definitely
Yeah, it's not a problem.
makes
Don't worry
makes
about it.
sense.
And
Okay.
hopefully, I made the other student feel the same way. I was a little worried when it first happened. It had sent me an email. I hadn't seen one from you yet, but yeah, it's a bummer when that happens. But hopefully, it won't be a big deal. We should be able.
Yeah, yeah, because I didn't see anywhere where it said that. I might have just missed it,
And that's
but
the other thing I'm
okay.
checking the video for because I typed it in to the respondus instructions. But if I, hit save or if the computer crashed before I hit save or something, y'all wouldn't even get those instructions. And if that's the case, I'll see that when I open it up and I'll know it's my fault, not yours. So there's some
Yeah,
possibility that both of you guys didn't know better because I screwed up or because the Canvas system screwed up when I didn't hit save or whatever. So there's
yeah,
some
okay.
chance it's my fault, not your two.
All right. Well, thank you so much.
All right, no
Yeah, just
problem.
send me an email either way. I guess send me an email if I need
Uh,
to redo it, and
yeah, I'll
if
send you an
not, I'll
email
see
either
it
way
in the
just to
grade
let you know
book.
what's going on. Yeah, that's
Okay,
cool.
cool.
Thanks, Jacob.
Thank you. Have a good afternoon.
You too. Anybody else? Looks like that's it. Vincent, you ain't there, bud? All right. Well, I'm gonna call it a day. Thanks for coming, everyone, and hopefully I can get these tests done soon. Now I have a couple other students that have to take it late, but we'll deal with that. Have a good one. Bye bye. Don't forget the online tests are going to change their date in the syllabus, and I gotta let you guys know about that when it happens.